So last section we started looking at standard free energy. We said that free energy was represented by the letter G, and it's going to tell me the complete overall change in energy for a reaction. So it will tell me whether a reaction is spontaneous or not. A negative delta G is a spontaneous reaction. A spontaneous delta G is not spontaneous. Now we said delta G depends on three things: the change in enthalpy, whether our reaction's endothermic or exothermic. It depends on the temperature we're carrying out our reaction, and it depends on the change in entropy, or the change in disorder. Okay? So when we're looking at delta G is looking at the change in energy as our reactants are becoming products. So we're comparing how much energy is changed overall for our chemical reaction. Okay? Now when we talk about standard free energy, it cannot be measured directly. There's no instrument that measures it. What we do is we have to calculate it. There are three different ways that we can calculate delta G. The first we already talked about. Delta G equals delta H minus T delta S. That's the most common, and that's what we'll usually use. Now, it applies only at a constant temperature. Now, what's nice about this reaction is it allows us to change the temperature and see how our reaction changes at variable temperatures. Okay? So here I've got my reaction. Carbon is a solid plus oxygen is a gas forms CO2 as a gas. I'm told that delta H is negative 395 kilojoules. I'm told that delta S is 3.0, this should be a 0, 5 joules per K. And I want to calculate delta G. Well, I know delta G is equal to delta H minus T delta S. Here's my problem though. Remember, kilojoules and joules. It's up to you what you want to do, whether you want to change kilojoules to joules or joules to kilojoules. It doesn't really matter. I'm going to change my kilojoules. So I'm going to say that this is negative 393,500 joules minus 298K times 3.05 joules per Kelvin. So when I calculate this out, negative 392,500 joules. My kelvins are going to cancel out. Or I can say it's negative 392.5 kilojoules. Either way works. Now it's important to remember that because I have a negative delta G, my reaction is going to be spontaneous at 298 Kelvin. It's not necessarily spontaneous at other temperatures. Okay? So here I've got a reaction, and it says I want to calculate delta H, delta S, and delta G using my information. Now remember, when we look at the tables, I had this fun little formula. My delta H was equal to the sum of the number of moles of my reactants times the H standard, products, minus the H standard of my products, minus the sum of my number of moles of reactants times the H for my reactants. So if I look at my chemical equation, I start with my products. I've got 2 moles of SO3. SO3 is negative 396. Okay. Minus my reactants. I've got 2 SO2s. So 2 SO2 is negative 297. Plus, because this is the sum, I've got 102. My 102 is 0. So when I plug this in, I've got negative 792 minus negative 594. So I get negative 198 kilojoules per mole. Okay? Take a second, do the same thing to determine your delta S. Once you know your delta S, use the equation above to calculate delta G. So remember, whoops, where'd it go? The delta G is going to be equal to your delta H times your T minus your T times your delta S. So solve for your delta S, make sure your units are the same, and then solve for your delta G. Okay. Delta G is a state function. Now remember, we talked about state functions with enthalpy as well. State functions do not depend on the path that's taken. We only care the initial state and the final state, and we're looking at the change. So way back when in the fall, we looked at Hess's law, and we used Hess's law to calculate changes in enthalpy. We can also use Hess's law to calculate changes in free energy. Okay? So here's my chemical reaction that I actually want to determine the delta G for. Now they give me 2 reactions below that already have delta G values. Okay? I'm going to use a couple highlighters to make life a little bit easier so that we can see how this works. So I want carbon monoxide as a reactant. So I look down here. Well, in the first reaction, I've got carbon monoxide, but it's a product. So what I'm going to have to do is I'm going to have to flip the reaction. I'm going to write it as 2CO gas plus 4H2O gas is going to form 2CH4 gas plus 3O2 gas. Now, initially, this had a delta G value of negative 1088. Because I flipped my reaction, I also have to flip the charge. So this is going to be a positive 1088. That's kilojoules. Okay? Now if I look at O2, I've got O2 here, O2 here. Since it's in multiple places, I'm going to just check O2 at the end and make sure it balances out correctly. So now I need to find CO2. Well, here I've got CO2. This time it's a product, and this is a product, so that's great. I don't need to flip it. However, I need 2 CO2s, and here I've only got 1 CO2. So what I'm going to have to do is I'm going to have to multiply this entire equation by 2. So now I'm going to have 2 CH4s. I'm going to have 4 O2s I'm going to have 2 CO2s, and I'm going to have 4 H2Os. Because I've multiplied all of this by 2, I need to multiply all of that by 2. When I multiply all of this by 2, I get negative 16O2. Okay? Now I need to make sure that all of this actually equals all of this. Anything that's the same on the left and the right of the equation, I can cancel out. Well, I've got 4 waters here. I've got 4 waters here. Those cancel out. I've got 2 CH4s here. I've got 2 CH4s here. Those cancel out. Now oxygen, I've got 3 here. I've got 4 here. So all 3 of those go away, and I'm going to be left with 1. So when I write everything that's left over, I'm going to have 2 COs as a gas. I'm going to have 1 O2 as a gas. I'm going to have 2 CO2s as a gas. And when I tally up this, plus 1088 minus 1602, my delta G is going to be negative 514 kilojoules. Now I didn't go the exact same route, but it doesn't matter. It's a state function. It doesn't matter if I do this reaction in 10 steps or 12 steps or 1 step. As long as I have the same initial states, the same final states, the delta G will be the same. So take a second, solve out example 8, use Hess's law to determine how much energy it takes to turn a diamond back into graphite.